Today's chemistry review video is over electron configurations, noble gas configurations, and orbital diagrams. First, we need to learn how to read the periodic table. So when you first start, you need to know what the letters of the periodic table are. When I say letters, I mean the orbital names. S stands for sharp, P stands for principal, D stands for diffuse, and F stands for fundamental. S, P, D, and F are orbital names given to the sections on the periodic table. A mnemonic device I use to memorize this is stupid people die first. That's just what my teacher told me. Something changes with the periodic table. La, the 57th element, and AC, the 89th element, moves from F block to D block. So now that I have told you the basic information, let's learn how to read the electron configurations now. So starting off, this is just like reading a book. You read the book from the top left of the page to the top right. Then you return under the first row on the left and read to the right again and again. We need to know that first S block starts with 1s. That's the top left of our page. Our page is the periodic table. You then read the first line left to right. So 1s is the first line and there's two letters across. When I say letters, I mean there are two s's across. You should write it like this. 1s up 2. 1s to the exponent of 2 basically. S will always go across 2 times. P will always go across 6 times, D will always go across 10 times, and F will go across 14 times. P, D, and F will start out with different numbers. Since S starts with 1, P will start with 2, D will start with 3, and finally F will start with 4. So a quick recap. S starts with 1 and goes across 2 times. P starts with 2 and goes across 6 times. D starts with 3 and goes across 10 times. And F starts with 4 and goes across 14 times. Okay, so now that we know the words to our page, let's read. Let me do an example first. I will be reading an electron configuration for iodine. For iodine, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. It's just like reading a book. You put words together to form a sentence. At the end, the reason why I said 5p5 instead of 5p6 is because iodine only goes across to the 5th box. If I was looking for xenon's configuration, I would end with 5p6. Wherever the element stops will determine the exponent number that you read. Let's do another example, but this time we will also learn how to write it. It's the same as if you were reading it out loud. Just write each word down. This one is going to be a little bit harder. Let's find gold's electron configuration. So start on the top left side where hydrogen is, and read to the right. 1s2 should be the first line you read. 2s2, 2p6 is the second line. 3s2, 3p6 is the third line. The fourth line should be 4s2, 3d10, 4p6. You keep going until you reach gold. So the fifth line is 5s2, 4d10, 5p6. The next line gets a little confusing. The next line should start out with 6s2. The trick is we don't go to 5d next. We jump down to 4f next. Earlier I said that La and AC moves to D block. The area they fill jumps down to F block. So not counting La and AC, I continue 6s2 to 4f14. And then I go back up to 5d. It should look like this when you finish. This is gold's configuration, specifically electron configuration. Now that we have talked about electron configurations, let's do noble gas configurations. It's similar to electron configuration. The only difference is that it's a condensed version. Sometimes electron configurations can get very long and time consuming, so this is a shortcut. So starting off, you still need to use orbital names. I'm going to use Mercury as my example. It's called the noble gas configuration because you start off with a noble gas. You might be confused because Mercury isn't a noble gas. To start off this configuration, you need to look for the noble gas that comes before Mercury. On the periodic table, noble gases are located on the far right column. That noble gas would be xenon, element 54. You would then proceed to write xenon in brackets. After that, you just continue a normal configuration like you would for electron configurations. You would do it until you reach mercury like before. So it should be xenon in brackets, 6s2, 4f14, 5d10. Here's another thing. Sometimes teachers or anybody will give you a trick question. They will ask you to write a noble gas configuration and give you a noble gas. You might ask yourself, how do I do that? Well, all you do is write the noble gas in brackets. That's noble gas's configuration. Super simple and easy. Finally, let's discuss orbital diagrams. You can only draw orbital diagrams for an element using electron configuration. You can't use noble gas configuration for this. So starting off, you need to know the Pauli exclusion principle. It states that for every 2 electrons, there is 1 orbital. S would have 1 orbital, P would have 3, D would have 5, and F would have 7. The number of orbitals are the number of boxes you will draw. No matter what, you will always draw that many boxes above the letter. Okay, I'm going to use titanium as my example. First, you need to write titanium's electron configuration. This should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. After you write the configuration, draw the orbitals above the configuration. It should line up with their letter. Again, S will always have 1 orbital because it has 2 electrons. P, D, and F will always have their corresponding amount of orbitals. You then want to fill the boxes. The boxes are the orbitals, so what you do is you look at the exponent, and then draw them in the box. There's a specific way you should go about though. My teacher taught me to draw arrows, one going up and one going down, like this. 1s2 has 2 electrons, so draw 2 arrows. 2s2 will also have 2 arrows. Always start drawing the arrows starting from the bottom left to the top, and then returning back to the bottom on the right and go up. 2p6 has 6 arrows, so starting at the bottom left, I go up. That only gives me 3 arrows, so I need to go back to the bottom right and go up, drawing 3 more arrows. An example my teacher compared this to is that P is like a house. P has 3 rooms. If P had an exponent of 3, it'd be like having 3 people in the house. So each person would get a room, but since P has 6 people living in the house and only has 3 rooms, each room gets 2 people, meaning 2 arrows. Same concept for the others. Finally, we have 3D2. 3D2 only has an exponent of 2, meaning that there is only 2 people living in that house. D has 5 rooms, so I would put each person in their own room, so an arrow per box. So that wraps up this chemistry review video.